All right, welcome everybody to the USC Viterbi School of Engineering Faculty Roundtable Series. I am your host. My name is Paul Ledesma. I'm the Director of Undergraduate Admission here at the USC Viterbi School. Today, it's my pleasure to be hosting a conversation with some faculty from our Aerospace and Mechanical Engineering department. And today we're going to be discussing everything related to aerospace and mechanical engineering. And there are no finer gentlemen to do that than the three that we have lined up for you today. I'm going to have each of them introduce themselves to you right now. We're going to get started first with the chair of the department, Dr. Paul Ronney. Dr. Ronney?
Hi, I'm Paul Ronney. As the other Paul said, great name you got there, by the way. I'm the chair of the Aerospace Mechanical Engineering department. I've been at USC since 1993. My main field of research is in the area of combustion. You know how a lot of kids go, maybe some of you go through the stage and like things burn or explode. Well, I never really grew out of that. Now I get to make a living doing that.
Fantastic. And Dr. Bermejo-Moreno.
Thank you, Paul, for the introduction, and it's great to be here. Welcome, all of you. My name is Bermejo-Moreno. I'm an assistant professor in the AME department. I joined USC in 2015 in October, and my research is on fluid mechanics from a computational standpoint. So I run simulations of turbulent flows, typically at high speeds in the supersonic and hypersonic regions.
Yeah, fantastic. And Dr. Spedding.
Hello, everyone. My name is Geoff Spedding. Thank you for joining us. I work in fluid mechanics also, but from the experimental point of view. And my main piece of research has to do with the aerodynamics of small-scale flying machines. These are drones or birds or bats and so on.
Or drones that look like birds or birds that look like drones or bats, etc. Awesome. I'm sure we're going to talk in detail a little bit more about that as we go. Folks, this is how today's session is going to go. I'm going to be leading the conversation for the first half of the session. We're going to talk all about the discipline of aerospace mechanical engineering. We'll talk about the curriculum, what you come to expect in the undergraduate experience in this department. We'll talk a little bit about research, and we'll also talk a little bit about what life is like afterward as an aerospace mechanical engineering student with these faculty. And then in the latter half of our session, I'm going to open up the Q&A feature to all of you, and then you all can ask your questions. And you will ask your questions. You also have the opportunity to upvote questions, and you'll push questions all the way up to the top, and we'll answer questions as much as we can going down that list. For the time being, I ask that you hold those questions. So please do not ask any questions right now. Hold those questions. We're going to have the conversation. I think it'll provide some more context to those questions later on and also kind of give us a guiding light to the conversation. But we'll get to as many as possible. The other thing I want to make sure that I outline is that today we're not going to be discussing admission or the application process. We have specific events focused on that where we can dive into those and handle all of those questions in detail. We'll put some information in the chat here in just a second that will outline how to sign up for one of those. If you have not signed up for one of our admission and information, our virtual information sessions for the Viterbi School admission process, please do so, because if you have any questions about that, that's where I'm going to direct you to attend one of those sessions. We have them twice a week, Tuesdays and Thursdays for first-year students and on Fridays for transfer students. But without further ado, let's talk about aerospace mechanical engineering. I'm going to start it out with probably the most simple seeming question. It's the quickest question, but it's probably the longest because it is going to be the hardest one to answer. What the heck is aerospace and mechanical engineering? Dr. Ronney, you want to give us a stab at that, and then others can jump in?
Okay, well, how about if I talk about mechanical engineering and one of my esteemed colleagues can talk about aerospace engineering.
Great idea.
This is actually an appropriate group here, since I generally teach the Introduction to Mechanical Engineering course that all the first-year students take, and Professor Spedding teaches the equivalent course for aerospace engineers. So I like to think of mechanical engineering as if something does not involve if something does not involve, let's say, flying objects, in which case an aerospace engineer will take care of it, or chemical reactions, in which case a chemical engineer will handle it. Doesn't involve electrons, in which case an electrical engineer will deal with it. Doesn't involve arrangement of molecules, in which case a materials engineer will fit. Then a mechanical engineer will probably be involved. Oh, by the way, if it does involve any of those things, a mechanical engineer will probably be involved as well. That is, I think of mechanical engineering as being the broadest of the engineering disciplines. I mean, every discipline says that, but in the case of mechanical engineering, it's actually true, because so much of what we do is the fundamentals, the core of what engineering is all about. I think of structures is a big part of what we do, thermal systems, energy systems, dynamics of systems, control systems. For example, so what is a control system? Say control that's kind of a negative term, right? You don't want to, no one wants to be controlled, right? Well, imagine if I wanted to balance my sunglasses on a point. In principle, I can satisfy all the laws of statics and balance it. The problem is it's an unstable system, because if it moves slightly out of equilibrium, it continues to go that way. So how do we do that? How do we control a system that's inherently unstable? Like modern aircraft, like high performance aircraft, are inherently unstable. Without that control system, it cannot fly and it will crash. And so, like I say, all these things permeate all their engineered systems. I give, as an example, let's say a computer. Say, well, that's electrical engineers or computer engineers. But what about overheating? You ever had a laptop that got overheated and shut down or something like that? Well, that's because they didn't have good enough thermal engineering. And I could go on about that sort of thing, is that so much of what we do in fluid mechanics, as the other two esteemed faculty members here study in great detail, most engineered systems have issues with fluid mechanics, even structures. You've all seen pictures or videos of the Tacoma Narrows Bridge. That wasn't just a structural failure, it was an aerodynamically induced structural failure. So again, what we do permeates more or less all of the engineering disciplines.
Shall I take a stab at aerospace?
Yes, please do.
All right. So aerospace is when you put wings on it. There we go.
Put a wing on it.
Maybe I'll elaborate just a little bit. But so Paul Ronney gave an example of his sunglasses. If we tried to fly his sunglasses with a pair of wings, then we'd be bothered by the performance and efficiency, and also the stability. Thank you, Paul. But very good. By and large, there are two branches of aerospace engineering. One has to do with flight in the atmosphere, and one has to do with flight outside the atmosphere, when wings stop working. And we have here an astronautical engineering department, as well as the aerospace part of aerospace and mechanical engineering. So between us all, we cover everything. And if you're interested in things that fly, then you'll be interested in the aerospace part. Aerospace engineering also has put serious demands on our knowledge of advanced structures, advanced control systems, and autonomy. And so you find many branches living in aerospace engineering that are at the forefront of, well, engineering in general.
Let me a quick tangent question or related question. A lot of our students that are here today also participated in the Astronautical Engineering Faculty Roundtable from last week. And not to make it competitive, but maybe I am. What's the difference between aerospace and astronautical? And while we're at it, I mean, what's the difference between all three of these: aerospace, mechanical, astronautical? And and which one's the best?
Well, we're the most awesome, obviously, but I should defer to our esteemed department chair for
let him fight it out.
response.
Yeah, well, as Professor Spedding said, if you're flying outside the atmosphere, then of course it's astronautical engineering. As it turns out, astronautical engineering is a relatively small department, so those students actually take a number of courses in aerospace and mechanical engineering as well. So there's not going to be that much difference in the first 2 to 3 years of your program, whether it's aeronautic on the aerospace side or the astronautical engineering side. Then at your junior and senior levels, you'll have some more specialized courses in one discipline or the other. And in terms of which is the best, obviously ours is the best. But as department chair, I have to be of aerospace and mechanical engineering. Obviously, I can't play favorites, but I would say that pick what most interests you. And there's enough similarities that, put it this way, if some potential employer or some potential graduate school says, well, I don't want you because you are an astronautical engineer, I really want an aerospace engineer, I think that's probably not a place you want to be a part of. They're too narrowly minded. So I would just say pick whichever of those departments seems to pique your interest. After seeing our webinars, hopefully you'll be able to visit campus and see some of the labs, talk to some faculty in person, and then make your decision based on that. But it's not going to be a big difference one way or the other.
Right, and your options coming out are not limited by one way or the other. And oftentimes you'll have, with one of these degrees, you're working next to someone with the other of the degrees. It's a relatively similar skill set, and so a lot of the overlap happens between the programs. I'm going to remind everybody, I'm going to keep dismissing questions that come in early because we don't have an opportunity to manage a Q&A right now. So please hold your questions for the time being. We'll get to the Q&A towards the latter half of the session. Let's talk a little bit about curriculum. Let's talk about what that program looks like. What does the undergraduate curriculum look like? I don't know if we want to do the same thing. Do we want to talk about mechanical first and aerospace second, or do we want to talk about it as a whole? Like what types of courses happen? What is that arc of the undergraduate degree program?
Over to Paul.
Okay. Let me show you. I have a couple. I'm not going to go through a presentation, trust me. But let me just show you. I have a graphic laid out here on that very topic. Okay, can you all see that?
Yes.
Okay. So basically the curriculum, you start with your basic math, chemistry, and physics, chemistry or material science for those of you that are sort of chemophobes. Although personally, even for mechanical engineers, I feel the one thing I wish our students knew more of was chemistry. Materials is very important, but it's all based on chemistry. Then there's your general education courses outside of Viterbi and outside of the sciences. You learn a number of tools. You learn about computer-aided design. You learn in your junior year tremendous amount about experimental engineering and instrumentation. You learn about using computational methods to simulate real physical systems. And then we have a number of core, what I call engineering science disciplines. I mentioned a few of those earlier. Mechanics. Mechanics doesn't mean how to fix your car, but talk about statics, that is structures that don't move, and dynamics, structures that do move. The strength of materials, beams, pressure vessels, fluid mechanics, as has already been discussed, thermal and energy systems, and control systems, as I mentioned. Last slide, I promise. And also, I should point out that within AMA, you will have a laboratory experience virtually every semester. Now that sounds, probably for most of you, that sounds great, but keep in mind though, that those laboratory classes and those projects, they take up a lot of time. So, I mean, to us, it's an essential part of the curriculum, but they do take up a lot of your time. Finally, then you'll have a senior level design project, we'll call a capstone design project, where all this vast knowledge that you've accumulated over the past 3 or so years, you'll use that to design a final project. There also, I want to point out a number of the enrichment, non-credit enrichment opportunities. You can do directed research with a faculty member, as Rosie behind me is well aware of. Excuse me. You can do directed research with a faculty member. We have a number of clubs. We have the Formula SA race car team and the aero design team, which I should say has won several national, actually world championships. We're sort of like the Alabama. What Alabama is to college football, USC is to aeronautics, and particularly the aero design team, or they call it the design, build, fly competition. We have a number of other projects, though, human-powered vehicle, solar car, etc. So I encourage all of you to get involved in some extracurricular activity. In fact, my recommendation is that you get involved in one of these kind of extracurricular activities that is related to your discipline, and then do one other thing that's totally unrelated to your major. Maybe it's marching band, maybe it's theater, maybe it's some sort of sporting activity, but something unrelated to your major. And I'll stop there.
Maybe another faculty member can jump in. One of the, this is probably not going to be a well-formulated question, but hopefully you can get where I'm going with this. One question we get a lot from high school students is, what's it like taking classes in college? Can you walk us through what one of your classes is like compared to their typical high school class? If they go to school, they go to that class every day at 9 a.m. Monday through Friday, and they're there for an hour.
Yvonne, why don't you?
I'll be happy to jump in, yeah. So the course that I teach for undergrads is called Fluid Dynamics. This is in the 3rd or 4th year, typically. And it's a mainly theoretical course, even though we have an experimental component. Now, probably the main difference with high school courses is that we are not teaching you a recipe on how to solve problems. We are teaching you about how to think so that you can develop that recipe for yourself. So you're going to learn about the physics, the fundamental mathematics behind the formulation of fluid dynamics. But then we're going to challenge you so that you're going to encounter things that you didn't see in class. And you have to brainstorm with your colleagues, you have to think on your own, and then try to develop a solution. So I will say this is, in my opinion, the main difference with respect to high school courses, where it's probably more of a recipe in terms of mathematics and physics. Of course, you need to develop the understanding also in high school, but in the college courses, it's going to be multiplied by a large factor. That independence that you need to gain to be able to solve problems by yourselves, and problems that you are not expecting. So things that are going to come from different new places. Maybe you have to combine fluid mechanics with your calculus courses that we have seen in previous years, or bring concepts from physics, chemistry, and so on. So it is that challenge that's going to be a critical aspect of your education.
Yeah, if I could add one thing there, as Rosie reminded me, is that one of the worst questions you could ask a faculty member is, what formula do I use to solve problem 3 in the homework, right? It's not all about, saying, was this formula, that formula, this formula. It's understanding the concepts, so you'll know which formula is appropriate, or if any formula. In a lot of cases, there will be no formula that's appropriate. So a good question might be to ask is this formula, does it, require incompressible flow or something like that? But just asking, which formula, it's not a matter of just plugging numbers into formula, which depending on your high school, you may have had a lot of that. It's not like that at all. We're trying to teach you to think like engineers.
Dr. Spedding, do you think you can jump in with maybe a class that you've taught in the past or currently are teaching, and how to maybe help our guests visualize this process of your class?
Yes, by all means. And to amplify the previous couple of comments, what's it like to be a student in aerospace engineering and mechanical engineering? I think there are two components. Paul Ronney talked about this a little bit. Every year there's a practical component. And so we believe very firmly in mixing theory and practice and computations. This happens not every semester, but certainly every year. This happens to us in practical life too. That's what we do. I just spent the last 6 hours of my life extremely happily programming. And it's not something you necessarily associate with aerospace and mechanical engineering, but we do it. And the students in my class in Intro to Aero have been doing that now for about 10 days. And what they're about to do this week is start to build a glider. In 6 weeks' time, they'll finish them, and we'll have a competition starting at 6 o'clock in the morning on the baseball field. And we'll see who goes furthest. But more importantly, who can make the prediction about their glider and how far it'll go and at what speed and things like that. So in our classes, in many classes, there are blizzards of equations and a lot of sometimes fairly deep analysis. But at the end of it, we're engineers, so that we need some practical outcome to this. And I think that this spectrum that we cover, from very theoretical work and solid physical basis to practical solutions to very practical problems, will it fly or won't it? Can I take on a carry-on or not? Is part of the core of what we do. And like I say, this enriches our curriculum every year, right? So from the first semester, you get an introduction to mechanical engineering, you get an introduction to aerospace engineering, and these specialized classes are mixed in with the more general classes every year of your study.
That's great.
Yeah, if I could,
please go ahead. Please go ahead.
If I could add one thing, so I have another prop for you. So here's in the freshman class that I teach, I have one slide for you, Jeff. So one of the things you learn about is the strength of materials. Another thing you learn is how to do CAD, computer-aided design. And so one of the projects in this class is to build or first virtually build a truss bridge. And then you will test it, not just, build it and say, that looks like that ought to be pretty strong. You actually then, by the end of the semester, understand enough about materials and about stresses and strains and about how to use the computer-aided design tools that you can actually test your bridge virtually. And these colors here represent different stress levels. Red means it's more likely to break. Blue means that there's not much stress acting on it, so it's less likely to break. And in fact, this group of students, this was from last year where everybody was remote, but they were able to do their design remotely. We on campus then 3D printed their bridges and tested them in person. We actually had a setup where they could actually, add the load and watch the load increase. And then as all of a sudden, as it starts to break, it drops off. They could all see that in real time. We had that via Zoom. So they learned really about the whole process of engineering, starting with specifications, going to brainstorming, going to computer-aided design, analysis, of the stress using computer programs to do that, then building it physically after building it virtually and testing it virtually, and then testing it physically, and then actually a whole cycle where they repeated that once, so that their final, this was like their initial design. Then they could see what went right and what went wrong, and then their final bridge could be even stronger. I asked them to predict what their failure load would be based on what this said. It was amazing how many of them hit their target almost dead on. I was really surprised. Somewhere within just like a couple of % of the failure load was almost exactly what they had predicted, which actually surprised me, considering that this 3D printing really kind of has this layered structure, which was not part of the analysis package that they had. So I'm surprised it worked as well as it did.
That's great. I realize we should probably pause for a moment, Dr. Ronney, and add a little context and address the elephant. I mean, address the horse in the room. I know that we're all kind of used to seeing you with friends behind you, but I realize our guests probably are not. Do you want to provide a little context as to what your Zoom situation is?
Yeah, well, last year during the pandemic, that I taught virtually all my classes here from the barn. This isn't our horse. Our horse is out in another part of the barn where the reception isn't that good. There's no Wi-Fi here, so I have to tether through my phone. And where our horse is located right now, I don't know if you can hear that or not,
Perfect
but I guess
timing.
everyone's getting anxious because it's about dinner time. But in any case, so I started having doing my lectures from the barn. This is a place that I could be, something more interesting than just being in the spare bedroom or something. And it was relatively safe, not much traffic. And so this year, actually, I had a gathering for my students from last year. And so we met at the barn, and I thought, oh, gee, they must be all anxious to meet me. Well, as soon as they got here, they kind of ran right past me and ran right to the horse. They didn't really care that much about meeting me, but they wanted to meet Cavalier, my horse.
So that's great. So all the students last year who got to see Cavalier over Zoom got to meet them in person. I saw the pictures that you posted. It looked like it was a lot of fun. And to clarify, when you say our, that's not USC Viterbi's barn or USC Viterbi's horse. You mean that is yours and or your family's?
It's really my daughter's horse. But
okay. Just want to clarify. I realized you were saying our, and I was like, the rest of us have nothing to do with this.
Up until the early 60s, I learned that there were actually stables on campus.
Oh, well, here we go. Awesome fun fact. Thank you. All right, getting back into it. Whoa, sorry, a giant thunderstorm just happened outside, and that is weird for Southern California, and I'm getting a lot of rolling thunder right now. I don't know if you guys are, wherever you are. Anyway, let's get back to what we're talking about. We're talking about the discipline, we talked about curriculum, we talked about classes. Let's talk a little bit about research. Can we talk a little bit more about the research in the Department of Aerospace Mechanical Engineering? What's new and exciting for Aerospace Mechanical Engineering? What's research you all have been involved in or are currently involved in? It's a broad question, whoever would like to jump in and take it.
How about Ivan? Ivan does awesome computations.
Ivan, let's go for it.
Sure, yeah, I'll get started. So what we do is in the simulation and numerical diagnostics world. So we want to be able to predict the flow physics that are related to flying objects or to objects that are entering atmospheric atmospheric environments, for example, in missions to Mars, in missions to Titan, and other planets or moons. So what we have to accomplish requires typically a high fidelity, and that requires high performance computing. So we need to know not only about the mechanics, about the fluid dynamics and all these physical aspects of it, but we also have to combine it with computer science and computational science. So as Professor Spedding mentioned before, we have to develop some skills in programming and be able to map the programs that we develop in very large computers here at USC or in the national labs at NASA and so on. So this is basically the bread and butter of what we do in my lab. So we have about 5 students and postdocs now working on different projects. Some of them incorporate not only fluid flow physics, but also solid mechanics in what we call flow-structure interaction. Others are dealing with the flow over canonical configurations, for example, a simple speed bump that you can encounter on the street, but that poses some challenges in the simulation of the fine scales of turbulence, and so on. So there is a quite a diverse set of fluid flows that we study with different applications. Our research is funded at the moment by NASA, 2 projects, and then Department of Energy, 1 project, and the Department of Defense for another project. So there is 1 undergrad student who is working on simulations of planetary entry, in particular in Mars, for future missions. So there is always opportunities for undergrads to get involved in research through the directed research that Professor Ronney mentioned before. And I'll stop here so that others can comment on the research.
If I can nudge things along then, I'd just like to make the point that aerospace engineering is exploding. Well, figuratively, it's exploding in the breadth and depth of new applications and new knowledge required to do the things that we want to do. So there's been an extraordinary development of manned and unmanned vehicles, of supersonic, hypersonic planes, of all kinds of flying devices in the last 10 years. And it turns out that our ambition exceeds our knowledge sometimes, and many times we don't quite actually know how these things work. And so part of what my research is trying to go beyond the simple paradigm, which is what we do at first, throw it in the air and see if it flies, and try to understand why it does or doesn't. And so I work on the aerodynamics of small-scale flying machines, where it turns out we know much less than we thought we knew, which is good news for those wanting to do innovative design. It's also good news for those wanting a job. So there's a huge explosive radiation of jobs around Los Angeles and around the world, actually, in aerospace engineering. A topic that I don't think we've quite covered yet is, should I plump for aerospace engineering? Will I be put into a small minority occupation where there are fewer jobs and things? It's not a small minority occupation, and there are tons of jobs. And the very important message that I have for you right now is to follow your dream. Don't stop now. Do what you like. If you like to think about flying rockets and satellites, if you like to think about destroying bridges, if you like to think about flying things, we all do long, hard hours of homework. We all work hard. We all solve many similar equations. But just keep in mind, the important thing to do is to have something that feeds your inner curiosity, that makes you excited, that you think will be fun. Because the main thing to do is to do well, get good grades, and then it really doesn't matter that much what your speciality is. So anyway, I've veered from research back to grades, but the two feed on each other, of course. And so we'll perhaps talk about that later. Over to Paul Ronney, maybe.
Yeah. Okay, I agree with everything that Jeff and Yvonne said. Although keep in mind, everyone who says, don't worry about the job, just go for your dreams. Everyone who says that has a job. So keep that in mind. But no, I do agree with that. And really, if you do what you enjoy doing, the jobs will come. They will come. In terms of my own research, I mentioned I do combustion, although I spent a large part of my youth trying to make things burn as rapidly and explosively as possible. Actually, a lot of what I do now is looking at the opposite end of combustion. What is the minimum that can burn? And say one particular application of this is, now we all have cell phones, right? And you think, well, but if Los Angeles, and unless you're a Tesla, and you became in a fuel-powered vehicle of some kind. So you say, why not a battery-powered aircraft, for example? Well, the battery, the energy density of batteries is just too low compared to fuels. So then why do we have batteries in here and not fuel? Well, what's funny is the same thing we do everywhere in the world every day is convert fuel to either electrical power or propulsive power or pumping power. The same thing we do everywhere in the world every day, or shaft power. We do everywhere in the world every day. We still don't know how to do it small scales. Now, many people have tried to take big things and make them small. So, and just take a gas turbine engine or a piston cylinder engine and just trying to make it very small. And they have failed every time because it just doesn't scale well for the same reasons that we don't have people the size of insects or insects the size of people, thank goodness, that we don't, things just don't scale that well. And one thing you'll learn about in any of these programs is about scaling and the importance of scaling. And in any case, so we're looking at ways of using either thermoelectric devices, that is, converts heat transfer into electrical power, or using fuel cells, which basically convert electrochemical potential into electrical power, and doing that on a very small scale in a way that would replace batteries, and things like cell phones. Now, I'm not trying to compete against internal combustion engines at large scales. I'm just trying to compete against batteries at small scales. Another offshoot of this work has been develop very small flying devices. Again, people have tried doing this using batteries or using either tiny gas turbines. Again, they've not succeeded. We're trying to come up with internal combustion ways, although I spent a lot of my youth trying to build internal combustion engines that would go faster, that now I find that for these small applications that that's not really the right way to go. So the bottom line is right now, small is big.
It's going to be my last question, and then we'll hand it over to our audience to start asking you all questions. And again, we'll use the Q&A feature and allow you to upvote things. So as I'm asking this question, you could start dropping your questions into the Q&A. And then again, take the time to read through all these questions and start to upvote them as much as you want. We will go down those questions in democratic order. So the ones that have the most votes at the top are the ones that are going to get answered first. Also, again, please, we're not asking questions about admission or application process. We're going to put you to our information sessions that we have. Michael can provide some information related to that in our chat so that you can see how to ask those questions in one of those other sessions. Let's focus on learning from our faculty today. My last question related to outcomes and careers. After their undergraduate years and spending 4 years with you all taking courses, where do our students end up? Where do they go? What happens?
Well, sometimes I think the first Hyperloop should be between USC and SpaceX, because we send an enormous number of our graduates to SpaceX. I mean, as well as the other aerospace companies, but SpaceX in particular, they love our graduates. But all the major aerospace companies, some of the automotive companies, consulting companies, it's really quite a mixed bag. But I will say that the local aerospace industry, as you might imagine, is a huge consumer of our graduates.
All right. Any other ideas?
Maybe I should add that the pat answer to that is everywhere. Our graduates go everywhere, and that's the case because they've done a hardcore, genuine engineering undergraduate degree, which is much valued amongst potential employers. And so, yes, we go to aerospace companies. We also go to finance companies and companies making cooking products and Lord knows what. And the idea behind getting an education here is that we teach you how to think in an analytical and innovative fashion so that you can then develop your own craft in a number of different ways.
If I could add just one thing, my two best students ever in terms of coursework, each of them were in 3 of my classes, and in each case they just blew the top off the curve. They were just like detached. Both of them are now patent lawyers and probably making more money than I do.
Ooh.
But still, that they developed that, that they had the technical expertise and the wherewithal to do what lawyers do.
Quick guess. Is one of them Gavin Moeller?
No, I didn't know about Gavin.
He's a lawyer too now.
Okay.
All right, let's get into our questions. Inamai asked a couple questions. I'm going to handle the first 2, but then I'll give it all to you 3. The question is how many students in Astro versus Aeromechanical and how many women? First thing is that we don't have locked in enrollments. None of our programs are impacted. So there isn't an exact answer to your question. It's not like there's one number here, one number there that's locked in. More specifically, I think there was another question later on, but there's no impacted program, which means you don't have a greater or worse chance of admission on one or the other. I know that's really weird compared to every other engineering school, but don't try to strategize your admission process. There isn't one that's easier to get into, one hard. They're both just extremely hard. The admission rate for the Viterbi school is around 9%. So just keep that in mind, that it's highly selective. It's not like you have an easier way, or just pick the thing that sounds the coolest to you, to paraphrase what Dr. Spedding was talking about before. The thing that sounds the coolest to you right now, and you're not locked into it. When you're admitted to one of our majors, you're actually admitted to all of them. And there are students that start in Astro and move to Aero or move to Mechanical or vice versa. That triangle, a lot of people move between them all the time. But roughly, each incoming class is roughly somewhere between 75, 80 incoming Aerospace Mechanical Engineering students, Astronautical somewhere between 15 and 20. That's rough.
More like, but between Aerospace and Mechanical, it's a little around closer to 100.
Again, this is where it depends on the year, right? It depends on the year, it depends on the app number. It comes in each year. Like right now, this incoming class was 86. So like it just really ends up depending. There's not a locked in number. As far as females students go, you should know the last 3 years, the incoming classes for the Viterbi School have been on par 50-50. This year, 50-50 again. And in Aerospace Mechanical, it's roughly 50-50. So that's exactly where we end up being. That's where we want to be, is on it with parity. But the question to the faculty, do you have to be very good in building things, very hands-on? And what is the quality to be successful? What qualities do you find to be successful in students for Aerospace Mechanical Engineering?
We always wish that students were able to build things, and we sit around and grumble about that sometimes, but the answer is that things that you need to build on campus will teach you how to build them. And so if you don't know how to build yet, then you will. And what qualities are required for success? I think you need two things. You need to be medium smart, and you have to have the persistence of a mule. You have to keep going. You have to be able to face adversity, know when to get help, and keep going. And so you'll find yourself surrounded by persistent colleagues. The other thing, of course, is talk to your fellow students. More and more, especially post-Zoom times, which I'm happy we're in, I'm finding that part of the joy of our enterprise, and I'm talking about research, teaching, everything, is in collaboration and getting together with people. And that's really been a key for advanced student success recently, is informing groups and solving problems together.
Yeah, if I could just add one thing, is that in my freshman class, in some majors, the students that may have a little difficulty are the ones whose math backgrounds aren't quite as strong. At least the way I teach my freshman class, math isn't quite so important, but it's really a physics background. If you haven't, most of you, will take a physics course, although we've actually had students that have taken 0 physics classes in high school. But I'd strongly recommend, if you have an opportunity to take more physics classes, I know that most of you are in your second to last semester of high school now, but if you have any opportunity to take extra physics classes, to me, that much more than math is the thing I would recommend.
All right, great. Kunal asks, are there any study abroad opportunities in aerospace engineering? There are study abroad opportunities for all of our majors, but the thing you should understand is that study abroad opportunities are not locked into specific majors. Aerospace engineers study abroad just the same rate that other majors do. We have opportunities across the university and specifically for the engineering school. Of course, all of that is on pause right now, but we're hoping to bring that, obviously, I hope for obvious reasons. Study abroad opportunities have been on pause for the last year and a half, but we're hoping to bring those back. I believe this upcoming summer, if not for the spring. So yes, you have many opportunities to do so. Balamir asked a lot about Calc 1, Calc 2, because, I've already taken Calc PC. Yes, there are certain credits that can come through. Check viterbiadmission.usc.edu/credit to see specifics about that. Michael, can you please put that link into the chat so we can outline that, but it's all lined up for you. If you have the credit and it is deemed equivalent with scores on AP exams, 4s or 5s, typically 5 on BC specifically, then you can advance into the curriculum and get into that next level, which we don't want to make you repeat something if you've already proven proficiency in that. Haley asks, any crossovers between Aero and Astro? Could you do both? And where would they apply together? We get this question so often, basically like, I can't choose, so can I just do both? That would be the easy answer for me. So how do we address this?
Flip a coin.
Space or no space?
Paul Ronney already said that many of our classes are common to both majors. It's probably a mistake to try to take both because they are so similar, and rather maybe take a music minor or theatre minor or something different. It doesn't really help answer your question, but pick one and see.
Yeah, I would be more blunt about it. Like, it's not a good idea at all to do that together. You can, but it's basically the same. I tell people it's like majoring in English and then minoring in creative writing. Like, just let's do one. And what Dr. Spedding said was flip a coin on where to start. Remember, when you're thinking about this application process, you're not choosing where you're ending, you're choosing an entry point. And that entry point means, like, I think this is it's the most applicable to me. And if you don't like it, then the next semester you switch to the other one and you have lost no time toward graduation because the curriculum is so much overlapped. I wouldn't worry about this at all. And if you get through your whole degree program, well, then now you know what you're doing for your graduate degree. You're going to flip the opposite, right? An aerospace undergrad, an astrograd, vice versa, anything in between. There's lots of mixes. And the skill set and what you learn is applicable across the board. Again, we've said this a few times. You're not limited by choosing one of these over another. Your options don't necessarily change. You want to work at SpaceX, they hire all of these people, including ones we haven't discussed: electrical, computer science, industrial systems, etc. Dr. Ronney, were you going to jump in? I think I stepped on something you were about to say.
Oh, you covered it.
Okay, good. As an undergrad student, are there any opportunities in participating in research or projects with companies such as Boeing or NASA? Jeff, you want to show them what shirt you're wearing right now? Cue the NASA shirt. So research, companies, involvement. Let's broaden it out as much as we can here.
I will say.
Oh, sure.
Elon?
No, go ahead, Yvonne.
Go ahead.
No, you first.
Okay, I was going to say that it's always possible. As I said before, one undergrad student is working on a research project for precisely NASA, and there is always opportunities to get involved. Usually, I would say for more serious research that you can accomplish goals that are going to matter for funding agencies like government agencies or companies. Typically, you will do that in the later part of your programs, but you can get involved early on in trying things out, I will say. The ones that are going to have implications for actual companies and funding agencies, that typically comes in the last part of the undergrad program. But yeah, you're always welcome to contact different faculty, try to reach out and get involved.
Yeah, I've had a number of students do internships at JPL or at NASA Glenn in Cleveland. So yeah, it's quite possible.
All right. Yeah, lots of partnerships. This question came up in the astronautical session as well. All these companies are involved in design reviews for student organizations as well. Don't forget that as an opportunity to work with these companies. But basically, yes, everything works along those. Felix is asking, what field of engineering is best to become an astronaut?
Well, some of you may know I was a backup crew member for 2 space shuttle flights back in 1997. My undergraduate degrees in mechanical, my graduate degrees are in aerospace. I feel I really kind of on the fence between the two. And to be honest, for the astronaut corps, and without getting into a whole long discussion about that, they're not really looking for people who are specialists in one area. They're looking for good generalists. So what I recommend to people who are interested in the astronaut corps, first of all, get an education and then go including a PhD. What field you're in, it actually doesn't even matter that much. It's just sort of showing, yes, I can pursue this. Also, I would say go into the military. If you can be involved in flying, even if you're not a pilot, either because you don't have the skills or your eyesight isn't good enough, at least be like a backseater in aircraft. Get that operational. The key word here is get operational experience, because astronauts are all about an operational experience. And also get some civil service experience. One astronaut that I knew, he had gone to the Air Force Academy. He flew B-52s. He then got a PhD in astronomy, and then had a desk job for the CIA, not a spy position, but probably like managing spy satellite contracts when he was chosen, because he had everything. So that's kind of what they're looking for. And one thing, they're looking for team players. Academics in general, we're not known for being team players. We try to be like we're all right here, but in general, we have to show our own expertise. So we're not kind of the antithesis of what a team player is, but that's really what they're looking for in the astronaut corps.
And just to give you one more sample point, one of my good friends from after my undergrad, actually, we started working together at the end of our degrees. He's from France, and now he's at the International Space Station as an astronaut. And his degree was in Aerospace Engineering. But then he started in space company like I did. Then he moved to Air France as a pilot. Then he became an astronaut. So this goes back to the point of you can be everything you want and more. So this is going to provide you with the tools to become an astronaut or to become an engineer at the space company or anything else beyond that. So
I went ahead and dropped a picture of Dr. Ronney, his official astronaut photo from NASA, so that you can have proof that he knows what he's talking about with his experience as a backup crew member for the shuttle into the chat. So hopefully you all see that. It says unnamed.jpg, but that's a picture of Dr. Ronney. Are you all
Hey,
here?
that was 25 years ago. So, you know.
I didn't date it. I didn't date it. Are you in the middle of this thunderstorm like I am? This is insane.
Not yet.
Right?
It looks very threatening outside, but
this
not
is
yet.
insane. This is one of the biggest storms I've ever been in Southern California. This is crazy. All right. Will asks, and I love this question. Will, thank you for this. What are some of your favorite experiments that you do in class?
Well, flying gliders, of course. So that's my total favorite for the Intro to Aero class. There's also a lab class that I've taught on acoustics. And that was one of my favorites because you have 15 experiments running all at the same time, each of them generating a different tone. And if you manage to get around the lab without going completely crazy, then you get a Scout's badge or something like that. So that's a fun experiment too.
in the
Yeah,
course
I
that
was gonna.
go ahead.
Go ahead.
Please.
Oh, okay. Well, say I have my props here. Okay, so here's, I mentioned already one experiment that we do in the freshman class. The other project are robot cars, and here's an example of what one group did for their robot car. I think you can see what they're going to do now. So I asked them, they had some compulsory routines. It's like ice skating. They have compulsory routines, and this was their freestyle routine. Okay, you know what's going to happen. I'll end it there so we can move on. Irish over here like that.
Perfect Winnie from that. There is a question from Sarah about how would you describe the average amount of coursework that aerospace students have? Sarah, you might be referring to, well, coursework, you can, I put a link, go check the chat. There's a link, you can see exactly the amount of courses that you have to take. So it's not an average, like these are the courses you have to take to get the degree. You might be talking about actual like homework. Maybe that's where you're getting to, like the amount of work that you have. And every class is different, and college is slightly different, but I'll let our faculty jump in on kind of what they get to. But the one thing I want to preface for you is that there's a big shift from high school to college. In high school, you tend to have about 35 contact hours per week where you're in class doing work, and then you probably do homework on the side, for lack of a better term, before you get it in. You have kind of a nightly routine. College is very flipped in that you probably have about 15 contact hours per week, but you should be doing extra work on top of that. And this is going back to Dr. Bermejo-Moreno's question before about learning how to adjust to that classroom and learning how to learn and learning how to solve problems without actually just memorizing things or accomplishing some sort of set of recipes that you've been assigned. So the work that you have to do is flipped, probably maybe 35 to 40 hours a week, but it's up to you. And each week is different, you know, as you go through the semester. So I don't want to take too much wind out of your sails, faculty, but specific work that you know the students have to do.
To me, the key element is to be on top of things. So you don't want to wait until it's too late to prepare for exams, to prepare for your projects. So try to be on a daily basis, working proactively to get to that point that you want, to obtain the grades that you are aspiring to get. And don't wait, because otherwise the train is going to catch up with you. So that's my advice. I tell it to all the students in my classes. Try to be proactive in getting to that point by yourself. And then reach out. So if you have any questions, reach out to the professors, reach out to the TAs, talk to your colleagues. So there is a lot of help that we can get. So don't wait until it's too late for that.
And we do have to work hard. You have to work hard. Engineers work hard. And you have to be prepared to be sharing an apartment with somebody who's not working nearly as hard as you, and somehow to be able to carve out your time so that you can do what you have to do. It's part of the game. However, I'm also of the opinion that it's possible to be an engineer and a human at the same time. And so I think that the successful person is able to budget their time to do things completely different from homework and engineering. And there is enough time for that if you're smart about budgeting the time.
Great.
And I'll say that I was going to say that in the projects that we do in my freshman class, after the project, they write a report. And one of the things I asked them to put into the report is, what would you do differently next time? And there are some technical issues, but the one thing that is universal, absolutely universal in these is they say, well, I wish we'd gotten started earlier. I mean, assign the project, and then they take a couple of weeks before they kind of, get their group together and start talking about how to do the project. They always say, we wish we had started earlier. The other thing that I would also say is do the simple thing first. Just try something. Just get, something that kind of works. You learn so much just by doing even the simplest possible experiment or design that relates to the project. So don't try to get everything perfect right, because if you do that, you're going to spend a lot of time, and at the end you'll flip the switch on, and you say, wait a minute, this isn't going to do what I wanted to do anyway. Why did I waste all this time doing this? So do the simple thing first. Make your mistakes quickly, cheaply, and in the case of combustion experiments, safely.
All right. I'm going to skip around our questions a little bit because some of these are getting repetitive. We've answered a lot of these. If you've missed any of this, the recording will go up on the website where you registered for this. You can go back and watch that, especially as we get into questions with companies and research. We've talked a lot about that. Haley, your question about AP STEM or engineering course, this is an admission question. It seems like a simple question. It's a long process about how we review applications. So I'd encourage you to come to our information session so we can provide a little bit more nuance and conversation to that question, because there isn't a straight answer to that, and I don't want to mislead you and cut it off short. So please come to that session, our info sessions. And Michael, can you please put a link to our info sessions in the chat, please, Michael, if you could put the link to our chat. Thank you. And then Kunal, that's basically a question I think we already asked. Colin asked this question: how do you see the industry of engineering changing in the next few years, specifically mechanical engineering? But since this is for aero and mechanical, what do you see the future of aerospace and mechanical engineering being like?
I actually have a slide for that too.
Oh, great. Perfect.
Yeah, okay, so let me pull that up. Let's see if you can see this. So let me say what's new, what's recent. I'm not going to make predictions. Well, I'll make a few predictions about the future, but as Yogi Berra said, it's hard to make predictions, especially about the future. But what is different now as compared to not that many years ago, 10 or certainly 20 years ago, this completely different, is one is, as I've mentioned before, computer-aided design. When I started out, everything was done on drafting boards. All these simulation tools. Nowadays, you don't just sort of look at something and say, yeah, that looks about right, and then build something and test it and see if it worked. You do a lot of simulation before you actually cut or build a physical piece of material. Also, when you build something, generally your first prototype, you don't start with a block of material and start removing stuff. You start with nothing and build it up in layers in 3D printing or additive manufacturing, as opposed to traditional machining, which you could call subtractive manufacturing. Also, nowadays we have so many sensors and actuators for everything. Your car has hundreds, literally hundreds of sensors and actuators to control everything in the car. And also, as Jeff was mentioning a little while ago, collaboration. We do a lot more collaboration now. We aren't as compartmentalized as we used to be. There's a lot more collaboration between different engineering disciplines, not just between aerospace and mechanical, but also electrical, biomedical, and all the other disciplines. So that's what's recently new. Again, I see a lot of this emphasis nowadays on, the sort of big thing that seems to be coming online now, artificial intelligence and machine learning, not just for the computer scientists, but in our case, AI, ML of things, not just for its own sake, But just think about like self-driving cars. Think about how far we've come along in the era of self-driving cars in just the past few years.
Great, thank you. There is a question. Hannah asks, what languages would you most recommend minoring in if you're an engineering major? I don't know if we have an answer to that. Do you have any insight on that, or minoring in general? I know Dr. Spedding, you were mentioning this earlier.
Yeah, Python. No,
I wonder
the one who
I wonder
wanted
if
to be
she
an
meant programming languages or if she meant actual spoken languages.
yeah.
Well, if you want to be an astronaut, then I would say Russian.
Like, okay, there's a straight answer.
Although I think Chinese, probably Chinese would be a good bet too.
I think from a broader perspective, if you're not talking about programming languages, first of all, there's lots of programming opportunities to take lots of different languages, especially through our information technology program, where you don't necessarily have to minor in anything. You just take these courses. But if you're looking to minor outside of the engineering disciplines, which I would encourage you to do so, Dr. Spedding was doing so earlier, these opportunities across the university aren't just languages. That's one opportunity, but there's also, the arts, cinema, political science, international relations. And it's not so much about what complements your degree the most, it's what complements you the most. What are you most interested in? What's exciting to you? Because your undergraduate years are your last opportunities to do those things. And that makes you a better engineer at the end of the day. Taking more engineering at this point doesn't necessarily do that. So let's absorb as much as we can from that interdisciplinary notion and do things that sound cool to you, not because you think it's actually value add necessarily. If it's cool to you, then it's value added. Okay, so we have taken up our hour, and I wanted to be respectful of our faculty members' times. Thank you so much, gentlemen, for being here. Dr. Ronney, Dr. Bermejo-Moreno, Dr. Spedding, thank you so much for being here.
Can I just
please, yes,
address a question that popped by in the chat box there? Somebody was asking about the class sizes, and I think it's probably worthwhile pointing out that that we have relatively small class sizes by design. And so Paul Ronney teaches the Intro to Mechanical Engineering class, and by now he probably knows 3/4 of the students by name and by sight. And I have about half as many in my Intro to Aero class, and I know about 3/4 of them by name and by sight. And this is one of the big important things about our department, is it's a personal and family type environment where we become introduced in the first year, and then we know each other for the next 4 years. It's a tremendously important and strong aspect of our department. That's it.
Yeah, if I could add just one thing onto what Jeff just said. I was a student at 4 different universities and on the faculty at another university before coming here. Of those other 5 schools I was associated with, none had this sort of sense of family and spirit that USC does. In fact, when I first came here and people were talking about this Trojan family thing and how important that was, I was like, yeah, okay, whatever. But I quickly came to realize there was really something to that. That's, I think, something that really makes USC unique, is this family atmosphere. It's all about what can you do for the family and what can the family do for you.
Thank you for that. I really appreciate it. And again, thank you all for being here and speaking to our prospective students out there. And for you all, if you have further questions, I would encourage you to join us at one of our virtual information sessions where we get to every single question. We don't cut it off at any point. And Michael put that in the chat there. So if you're a first-year student coming out of high school, register there at that link. If you're a transfer student coming from another college or university, please register for the transfer information session. We are looking forward to talk to you more further. If you have any other questions beyond that, you can give us a call, you can send us an email. We'll follow up this with an email as well, so you can watch the recording in case you missed any part of this. And if you want to join us at any other of our faculty sessions, go right to our website where you can register for any of the other ones or watch the recordings that have already happened. And we have student-focused events. So we have our students doing live chats on every other Sunday evening, focused on different types of student populations and different discussion topics. So you can get to know students. So far, you got to know faculty, you get to know us in the admission process, and we look forward to seeing your application. Make sure you get your application in no later than December 1st. Thank you so much for all of you that have joined us. We look forward to seeing your application real soon, and have a great evening. Fight on, everybody.
Take care.
Thank you.
Thank you, guys.